Hello, my name is Joe Royer, and I'm here with Mike Figlio, and we're going to present on advancing geopolymer rehabilitation across North America today. A few quick notes. All the attendees are on mute. If you have specific questions, you can put them in the question box on the GoToWebinar system, and we will answer as many of those as we possibly can at the end. This broadcast is being recorded and will be made available if people are interested in it later after it's finished. There will be a survey at the end of the presentation. If you leave the webinar, you'll get a survey. You will also get one by email. Any questions we can't get to, we'll try to follow up with email afterwards from there. And I think that takes care of most of the introductory starting points. So Mike's here with me. Feel free to introduce yourself, Mike.
Good afternoon, or I guess good morning to some of those of you on the call likely. My name is Mike Figlio. I'm a senior estimator with Michels Inc. with specific focus on our rehabilitation technologies. So what does that mean? We install Geopolymer, Geospray Geopolymer. We install CIPP, slip lining, any sort of rehabilitation technique utilized in underground infrastructure. Those projects cross my desk. I handle constructability reviews as well as the final pricing.
And my name is Joe Royer. My background's in chemical engineering. I'm the vice president of R&D for critical infrastructure, which includes the GeoTree solutions. So in GeoTree and with Geopolymers, I've done all the testing and the work on how to do the engineering, which we'll talk about later in this talk, a lot of the materials development, as well as quality control, site support, customer support, and a lot of other activities. So our contact information is all at the end, so feel free to reach out if you have questions to us, and from there we'll get started. There is an agenda on this. There's also an agenda on your GoToWebinar system. It's in the handouts if you want to follow along a little bit. We're going to try to cover the topics listed in here, a brief introduction, kind of an overview of geopolymers themselves, the materials, the advantages of the materials, design methodology, quality control, and some specific applications. Mike's then going to talk about all the details about product application, how it's done in the field, and some specific case studies, and then we will have some questions at the end. All good? Then Mike's going to give a quick once over on Michels, and then we'll get started.
Yeah, so as I mentioned, Michels Trenchless, we've separated into, not separated, we're the same company, but we divide ourselves and talk about ourselves in two different categories, rehabilitation and new installation. So new installation, as you see on the screen, the HDD, direct pipe auger boring, micro tunneling, essentially meaning we're using trenchless methods to install new infrastructure, where, as I mentioned in the intro, rehabilitation, we perform a number of different technologies in gravity pressure applications, UV, curing, thermal curing, as well as our SIPP group and slip lining. There is existing infrastructure. We're fixing it. We're rehabbing.
Sounds good. So I was trying to figure out how to move it. As I said earlier, I work for Critical Infrastructure, which is really a materials company. And Mike's going to disappear and come back when it's his turn to present the rest, which is a materials company focused on making materials primarily for rehabilitation products. We have 4 divisions. If you have questions on any of these topics, I'm probably your starting point for these, but our CSNRI division makes composite wraps primarily for oil and gas external pipeline repair of steel pipelines. We have a company that we refer to as Advanced Valve Technologies, or AVT. They make drinking water insertion valves. GeoTree makes our civil infrastructure repair products, primarily our geopolymer systems, but also some composite systems. And Fife makes, again, FRP strengthening materials for fixing buildings, bridges, as well as drinking water pipes. So with that, all of the introduction stuff is out of the way. Again, if you have questions as we go through, feel free to add them into the question box at any time, and we'll get to them at the end. So to start with the basics of geopolymers and what we're doing, these are spray applied systems that we are applying to a host structure. So you spray a new host pipe, new lining inside the system, and that new pipe is basically what you are creating inside the old structure. When we talk about geopolymers in specific, what we are doing, those materials are sort of a unique class. The first thing we like to tell people is people see the word geopolymer and the first thing they think is polymer. Well, polymers really are a class of materials that mean long chain molecules, and we won't spend too much time on chemistry, but they do not, the word polymer does not mean plastic. So often people think, hey, that's a polymer, that's a plastic. Those two words mean slightly different things. Polymer means long chain, plastic means the way it deforms. And so people put things like plastics like HDP, PVCs, and epoxy into a category. We are not those things. We are inorganic materials instead of organic. The inorganic materials are carbon, like HDPE is a carbon-based system. These materials are calcium and iron and aluminum-based in general, and silica. They look and feel like cements, so they have kind of the workability of cements, and you would measure the same sort of physical properties and those issues, but they have the chemistry of more like a natural stone that are monolithic, durable, and we'll talk a little bit later, corrosion resistant. Geopolymers are today sold into a variety of markets, the primary one being pipe rehabilitation because they have significant benefits there compared to standard cementitious materials. They're also used a little bit in transportation and tunnels, in bridges and commercial applications, primarily around patching materials and cement repair. The specific product that we market is called Geospray. There are a class of materials in our Geospray family that we will talk about. We talked quickly about these having cementitious or cement-like physical properties. So the properties you see on the screen are really related to things that you would measure in cements. I wanted to highlight a couple. So in the market of pipe repair, it's really a standard that the compression strength of the materials are approximately 8,000 PSI minimum. That's a kind of across the board standard you will see. There's some good benefits about that. Those are very high strength materials. We'll talk a little bit about quality control later. You have to be a little careful when you test stuff that has that high enough compressive strength that you do it right, but those are kind of the industry standard. When you think about cementitious materials, the general rule of thumb is that if you take the compressive strength, so in this case, the minimum values of 8,000 PSI, you would typically see a flexural strength somewhere around 1/10 that. So you would be expecting to see a flexural strength that's more like 800 PSI, and you would expecting to see a tensile strength also 1/10 of that. So typically around 800 PSI. And you can see here that the tensile strength of Geospray is around 1/10, 800 PSI. That's the value at the bottom of the chart. You can see the flexural strength value is almost twice that. And that has a lot of advantages in the design properties, as well as a few other places that we will talk to when we get to that point. So in addition to just our standard Geospray mortar, we do have some other systems that are available. Primarily, we have a product called Geospray HCE, which passes the most aggressive chemical resistant tests for cementitious systems. And we'll talk a little bit about that in the rest of the presentation. And in some cases, these materials are in contact with drinking water systems. So there's a picture, Mike's going to talk about a case study later of some tunnels in San Diego where these are with treated water. They're gravity tunnels still, but sometimes you will need drinking water certification. So we sell a product, Geospray 61, which has immediate return to service, NSF 61 certification for for pipes greater than 7 inches in diameter. So one of the main advantages of a geopolymer, and specifically Geospray, in addition to its flexural properties from a design standpoint, are the fact that it bonds to itself really well. So people that are familiar with cement is what we would refer to as a hydration chemistry. It brings in water, and that is what holds the material together. If you want to do a quick test, take a piece of cement, put it in your oven, get it up above 212 Fahrenheit, drive off all the water, and the next day it will be a powder. And that's because the water is really holding all of that together. In geopolymers, it's different. The actual molecules react to one another and make kind of a long chain. And when you have a joint, that joint is really still an active reaction site, and you can bring new material in contact with it and react through the joint and get a very strong joint. In this point, we would call it a lack of a cold joint. So to show kind of an example of that, we did a test with some 2-inch by 4-inch cylinders where we cast the bottom half of the cylinder on day 0 at a 45-degree angle. We then cast at various different times the second half of that cylinder on the top with no other preparation than other just dampening of the material. And then we tested everything after the top half of the cylinder had 28-day cure. And you'll see what happens is that in the pictures here, the ones on the top are from the Geospray samples. The ones on the bottom are from a standard Portland-based mortar that's available in this marketplace. And you can see that the Geospray samples, you can see the joints pretty clearly because the color variation of the samples is not always the same. We don't quality control for color, so you can see a little variation from the day to day. But you can see that the joints are not where it's breaking, which means that they're as strong as the rest of the material. And that's a benefit of these things specifically because in almost every case, you are applying multiple layers together. And this is really due to the specific chemical nature of this product. And again, I will just comment, if anybody has questions, feel free to type them in the chat. We're happy to answer them at the end. These materials, one of the other key flexibilities of this technology is its ability to be applied in a variety of situations. So I think Michael gives some really nice case examples at the end, but shape is not as big of an issue here. And in fact, if you have a pipeline that has different shapes, where it's going from egg shape back to round to a box, back to something else, you can line straight through those things because you can do them by hand, or you can make a small adjustment because you are really building this liner in place. You can do short lengths, you can do long lengths, you can do long segments. We're going to talk about a project at the end where we're actually, doing 5,000 feet between access points, 150 feet underground, so it gives you some of the real challenges. You can do as low as 24 inches. You can probably do lower. 24 inches is generally not in the most cost-effective zone for this technology. The bigger you go, the better it gets. We've done to date up to 20, 22, 25 feet. And you can have varying diameters in a single run. You can use structures that have high ovality, and you can repair structures that are boxes and other systems. You can have missing inverts in these systems. All of these things can be repaired, various geometries. There's the first picture here shows kind of a outfall with multiple geometries. All of those things can be repaired. The other key advantage of geopolymers compared to standard cementitious materials is their corrosion resistance. And what we have up on the screen here is an example of the mechanism that occurs in the sewer with H2S gas. So H2S gas is generated either by turbulence or by, through anaerobic biological activity in the sewage itself. It releases the H2S gas. The more turbulence, the more disruption of flow, the more gas release you get. And that gas is then absorbed by a series of microbes on the surface and converted to sulfuric acid, which then works to convert the pipe to a degradable material of gypsum. And you see that's how, you can see kind of the corrosion above the water line in that case. There's a more recent ASTM standard, C1894, that actually does a really nice job if people are interested in explaining the actual process of how this corrosion goes about and the different stages. These materials are applied in situ, so they start with pHs in the 11s. It says 12 to 14 here. They tend to be a little lower than that, but they can be fairly high. There is multiple stages of basically biogrowth in stage 1 and stage 2 that are lowering the pH of the system to allow the correct microbes that are necessary for corrosion to really occur in stage 3. And this can be a process of time and depends on your gas concentration and your sewer conditions. If you have a concrete sewer, this is kind of what's happening in those systems. When we talk about testing, and we talked about earlier with the Geospray HCE product, there are a variety of tests that have been proposed throughout North America. Many of them have significant drawbacks. Specifically, they don't have standard solutions. They're really they're generic test methods that aren't really specific for sewer applications. They have different material sizes, different sample sizes. They don't always specify how much liquid you need compared to your sample size. And so comparing between manufacturers and comparing data can be a little bit of a challenge, which is why we like to recommend the German DIN 19573 standard. It is really a true standard. It explains all of the things that you need to do. If you do this test more than once, you get repeatable data. We've shown that in our testing, and they've got a long history of that. It has 3 test levels and 4 certification levels. So you don't have to make a decision between one material and the other based on some small data difference. You can specify the actual certification level. And that certification for levels 1 through 3, so it's listed here as XWW1 and XWW3. Those are abbreviations for some long German words that I'm not going to try to pronounce. But the pH, they do a pH of 4,000 hour soak where the material is constantly controlled to a pH of 4. And in that case, they measure the level of corrosion and they rate it in one of those 3 categories based on the loss of material, and they kind of rate it for a given value of 1, 5, or less than 10 ppm, which is shown in the chart. The highest level is XWW4. They do 2 tests there. They do a pH 0 test for 14 days, and they want you to maintain 55% residual compressive strength. And they do a pH 1 test for 70 days. Again, the pH 0 is adjusted back every day to the original strength with an excess of acid. They would adjust it. The pH of 1 is computer controlled, so constantly adjusted. The only reason the pH 0 isn't that way is because the pH 0 eats the pH meter, so you have some limitations on the capability of controlling it. But the pH 1 is a 70-day test, and you have to maintain 75% residual compressibility. It's a pretty straightforward test. It's well documented, and it gives you a good view of what are the real corrosion behavior of the system. So with that, we thought we would talk a little bit about design methodology. So when we talk about design of these systems, unfortunately, there is not a standardized design methodology that has been agreed to amongst the industry, but there is a lot of test data, and we have tried to do our best to do that. So the goal we view is a little bit of this guy on the tightrope. Our goal is really trying to avoid too much risk. We want to make sure that we are doing a design that is reasonable, that is conservative, but is predictive of what's really going on. And so with that, we have proposed the following sort of design methodology. We have taken all of this information from the mechanics of buried pipes from Watkins and Anderson, so we're not like stealing information. It's pretty clearly written there. But what we're designing to is the first crack of these materials. So what you'll do is you'll put a load on a system. We'll talk about the data in a second. You apply a load, and these pipes will crack across the crown as their failure. Everything has a failure mode. We're just trying to test what this one is. So you get a stress at the crown, which is the stress of cracking, which in our view is equal to the flexural strength of the material. We set those equal to basically a standard moment analysis of the system with thrust. And we have assumed in this case that the thrust is equal to 0, that the neutral axis is at the lining, which you see here is the C/T, and that we use the standard section modulus. That will reduce to the equation you see on the screen, where you can determine the thickness based on the load applied P, the radius of curvature at the crown of the material, and the flexural strength, and then you can apply safety factors to your load as necessary. So you don't have to take our word for it. There is a bunch of options here on various tests that have been applied. Specifically, there are, as far as we know, at least 5 studies. All of these are now sort of published because we've published all of this information, at least for our material, where it's available. But there was a study done in Malaysia in 2013. Ian Moore at Queen's University did a study in 2015 where he buried some pipes and corrugated metal pipes in his laboratory that were exhumed from the 407 highway and tested those. We did a significant amount of work with Louisiana Tech and the trenchless technology, where we have written several papers of both corrugated metal and concrete, reinforced concrete pipes that were repaired. AASHTO, in what used to be called NetPep, is now called the Transportation Audit and Product Approval or Evaluation Program. I'm not exactly sure, but they have, material manufacturers have put data or have had data tested through their standard laboratory process, which is for available through Datamine to anybody that's a DOT or a member of AASHTO's Datamine group. You have to be a group for that, but we have our data. There are other manufacturers' data that we don't have, but those aren't published. And then UT Arlington did a series of studies where they did corrugated metal pipes without inverts that they studied in 2001. That was not with our material, but we're going to incorporate all of that data into this analysis. What we did, and if you're interested, there's a very detailed paper from both ASCE Pipelines, and there's another one for NAST through No Dig North that goes through much of the details of each of the studies. And what we did in this case is we tried to calculate what we called the liner design pressure, which was actually applied to a tested sample. And then because we knew the pressure, the radius of curvature, and the flexural strength of the material, we solved for, or we knew the thickness, the flexural strength, and the radius of curvature. We resolved those equations for pressure. And what you will see here is this is the pressure that we measured versus what we predicted it should be. And anything that's below this line, a slope of 1, should be a conservative solution to the data point. So what we normally tell people is that as long as, and these are in scientific units, so 1 MPa is approximately 145 PSI. So as long as the design pressure is below 145 PSI, you get a reasonable prediction that's very conservative, or that's reasonably conservative for your design. If you are above 1 MPa, there is a lot less conservativeness, so we would recommend doing a different type of design. But when you start looking at the design pressures applied to a pipe, there is no live load that you can legally use that would get you to 1 MPa or 145 PSI, and you'd have to be 50 to 60 meters deep and be taking all of that soil pressure, which for a rehabilitation job where the soil should be reasonably arched is probably not a reasonable condition. So in reality, almost every reasonable design condition falls under that less than 1 MPa. And so these have kind of been the ways we have recommended people do design. And like I said, all of this is published. You don't have to take our word for it. For people that aren't familiar, there is a group based in the UK called the Water Resources Council, and they issue approvals. They were the original designers of the methodologies for how to develop and design CIPP with their type 2 method and their sewer manual. Our material is the only one that has a WRC approved alternative design methodology that they have vetted and published, that they have reviewed and agree with the design approach that we have taken, and that it's reasonable for these types of pipes. So all of that's available. In addition, like I said, there are multiple publications, many of them available through NAST, that describe all of this information. And if anybody is interested in having that conversation, we have additional webinars on design on our GeoTree website on demand if you want to go through any of that. Unfortunately, you will have to listen to me, but it's available. Real quickly, we wanted to talk a little bit about specifications. So as a bit of a commercial for our friends at Nasco, if people are not aware, Nasco has published as of, I believe, October or November of 2022, a spray applied liner mortar-based systems performance specification guideline. So it's a generic specification that covers how to specify these products, what the physical properties should be. They've been sort of bought off by the industry as a base level specification. It's been developed by the Pipelining Committee of Nasco. It's been approved by their Technical Advisory Council. It's free to download. So if you are looking to specify a product, this is a good place to start. We always have some recommendations that it is a pretty basic, straightforward standard, as you have to publish and get everyone agreed to. But if you have questions about that, we certainly would be available to talk through some of the ways you could improve that. If you are looking for who's been doing work with geopolymers, most of the major metropolitan areas in North America, everywhere from New York to Houston to LA, have stuff in the ground. All the way through Canada, in both Toronto and Edmonton, there are specifications. There are specifications in Asia. There is a significant amount of people that are doing this sort of work. There are pretty good specifications out there, and they're available. And there are also materials that are approved by WRS, which is really a overseas non-North American issue, but for drinking water, also the NSF 61. Also, WRC has reviewed these things. Also, they've been used in some mine safety applications. So there are specifications available from these major metropolitan areas. If someone is interested in, hey, I'd like to mimic the spec in Chicago, or at least like to start with that, DC Water has a very good one. All of those things are available, and we can help you find contacts to get that information if we can't just send it to you directly. The last section that we wanted to talk about specifically with these materials, this is a little bit more on the application side, but we wanted to talk a little bit about quality control. You know, normally we might cover that at the end of that, but instead of flipping back and forth between Mike and I figured I would take it here. So what we would talk about, when you do these jobs, there are multiple things that you can measure for quality control. One, you should be measuring or quantifying the thickness of the lining that's being applied. Our normal recommendation would be to vary some depth gauges that you can see disappear as you pull back your sled or as you apply material. If you have to, you can do a small drilling. We really like to stay away from coring, because then you have really created a fairly large hole in the lining that you have to go patch. It's doable, but nobody likes to do it, and you won't get samples that are testable because the liners are typically too thin to get a good coring for actual quality control testing. But in general, people are measuring a variety of properties. We really like to recommend, if someone is measuring compression, that they do cylinders. They can do them through ASTM C39. You can do tensile tests with the same cylinders, another set of them. but a same example cylinders through C1469. You can use mortar cubes. We like to stay away from mortar cubes as best we can. They actually give higher values, which from our view is a less conservative quality control measurement. So I think that you would be interested in pushing those things towards cylinders, which is what we normally recommend. And then when you measure flexural strength, typically these are measured on 2-inch by 2-inch by 8-inch beams for mortars. And we can help people with that. There are multiple tests for measuring flexural strength. They are not all the same. The one in the picture shown is ASTM C78. The key, this is what I would refer to as a 4-point bend. ASTM would refer to it as a 3rd-point loading, which means in this case, you've got 2 points on the bottom and 2 points on the top. Those 2 points on the top distribute the load in thirds. That's why they call it 3rd-point loading. 293 and 348 are center point loading or 3-point bends. Those actually give significantly higher results. So comparing between C293 and C78 can't be done. That's why we recommend, and Nasco has this in their specification, and most places have put it there, that you use C78 because it always gives you a lower value, which if you're using this for various things, it would be a good concern, a good conservative estimate. Finally, I would say your quality control is only as good as the samples that you take. Here's some examples of some various quality control samples that we've seen from the field. The one on the far right is what you would love every cylinder to look like. That's actually out of our own test lab in Colorado. You don't see very many bug holes. It looks pretty good. The sample on the far left, you can see that the person that was making the sample waited way too long, and the material was already curing when they tried to push it into the sample, and they were not able to properly rot it and remove materials. The same goes for the one in the middle. So the good news is, even when you've done things like that, they often are pretty forgiving in compression, and you get some reasonably decent data. But you can see the ones on the left are broken down the middle, across the top. That's because they were tested in tensile, and those will give you very poor values if you attempt to test them in tensile that way, because these samples are not of good quality. So you really want stuff that looks like what's on the right and not so much what looks like on the left. So when you're out in the quality control, really make sure you have a knowledgeable person taking samples, and nobody wants to come off the job site and say, hey, my quality control is failing. And when they are, usually we see things like this, which is really not a material problem. It's really about sample quality. We also recommend, from a quality constraint point, look, your contractors or your inspectors, if you're a municipality, should really be trained on what they're looking for. NASTO has some really great tools for this. They've outlined a lot of these things that are industry association approved, and we would recommend looking at the PACP and the ITCP training, but you really need to understand what you're looking for and making good samples. So with that, I'm going to turn it over to Mike, and he's going to talk about some of these actual jobs. It's all yours, Mike.
Yeah, thanks, Joe. And just as I switch screens here, wanted to verify that you can hear me okay?
I can hear you, yep. I saw a few people were having problem with their audio from the questions. I don't know if that got resolved, but I'm hoping everybody's hearing us.
Yeah, and the other thing I'll just add to that is, you know, I see a couple folks may have their hands up. Just a reminder, maybe you're hearing this for the first time if you jumped on a little later. Feel free to submit any questions in the chat. Joe and I will address those at the end of the presentation. Joe, can you see my screen?
I can, so you're ready.
Perfect. So just to further my introduction, I guess a little bit from earlier, maybe why I was asked to join and speak with you all today. As I said, Michels Trenchless, we install various slip lining products, cement mortar lining, epoxies, wide variety of CIPP. So we're pretty well versed when it comes to comparing the products, in addition to the geopolymer and that constructability review, the product evaluation. What I can say is that I can't stress enough the importance of finding the right product for the right project. So with that, on here, Joe talked a fair bit about the flexibility. I take that one step further. Flexibility from the contractor's perspective helps mitigate risk. So as we're evaluating various projects, we review a number of different factors, and that's beyond the obvious. The hose pipe is in poor condition and needs to be repaired some way or somehow. We're going to be looking at the requirement or the level of effort that needs to take place for the hose pipe preparation, bypassing constraints. It includes the fluctuation and volatility and flows that the system sees, what the overall project footprint is, how that can impact the environment, any other third-party interested folks as well, and the overall project constraints. So what I've seen with geopolymer over the years is that the application in large diameter sewers, Joe gave you the range of diameters, but typically as you get into the 48-inch diameter plus range, especially when you get into 72-inch and greater, the footprint associated with geopolymer as compared to many of the other technologies is much smaller. It gives you the flexibility. You're able to work within different bypass constraints. We'll look at a couple of those with some of the project profiles later. So this all leads at the end of the day to the goal of the product in the marketplace, to being the lowest cost, most effective solution. With any of the products, it starts with preparation. So here's a video of a typical smaller diameter, I think 30-inch if the video is correct, cleaning process. It involves jetting, removing the debris from the bottom of the pipe. I like this video because it's the first one I could find that had a deposit. So as the camera or as the jet head moves back in the video, there was a deposit on the bottom that would be something that we would look for. So we're going to look at all of this, and primarily we're looking for things like deposits, we're looking for cracks, we're looking for structural constraints with the material, other things that need to be prepared or repaired prior to beginning the application of the geopolymer product. Identification of active laterals is just as critical here as it is with others. One of those items is, of course, infiltration. So what you see on the screen are common terms utilized to describe various severities of infiltration from weaver to gushing. What you will see in the different geopolymer manufacturers' recommended installation procedures is references that include the elimination of running water prior to application of the geopolymer. This phrasing is often misinterpreted in some of the communities and with some of the owners and engineers that I speak with. But it really, the intent of the terminology is to allow the geopolymer to cure. So if the infiltration is such that it's just washing away the material as soon as it's applied, we obviously have to handle that first. But that doesn't mean necessarily that the entire pipeline needs to be free of infiltration in order to apply the material. An example I like to use is with brick sewers. So if you have ever seen a large diameter brick sewer, it's almost positively going to be leaking in some area as the mortar has failed and the groundwater infiltration makes its way through. If you have a firm stance that all the infiltration has to be removed prior to beginning the application, you're going to spend a great deal of time, a great deal of energy, and a great deal of money grouting the entire pipe. Although there may only be one runner 50 feet away from the access point, you may just continue to chase that all the way down the pipe. So the flexibility, again, with the product and Geopolymer is such that you can apply the material, whether it's first pass, partial coat, or the entire thickness, everywhere except for where that point of infiltration is, and then focus on an isolated area rather than the entire pipeline, because it's effectively sealed everywhere else where the geopolymer has been applied. So the next slide, we'll talk about the grouting process a little bit. You know, and this, in and of itself, this could be, I'm sure they are out there, there's a myriad of different ways to grout pipes. What you're going to see in the video is a smaller diameter hydrophilic system. It's the best video I can find at the time. So this is a Avanti product, the AV100 that's being mixed and used here. But these, like I said, these products can range anywhere from hydrophilic solutions, as you see, to hydrophobic solutions. Much like the technology used to rehab the pipe, the grouting process, the infiltration control process used is very site-specific. I would say even more so site-specific, because if there is a brick sewer and it's 3-course, it may require one level of control. If there is a corrugated metal pipe and it's coming through the bottom, that may warrant more of a hydrophobic foam. So again, this is a webinar all in of itself. It's over. Now we get to the actual casting process. Now, again, keep in mind, I can't really jump back and forth from slide to slide. These may be happening simultaneous to filtration control, but certainly after the cleaning has taken place. Spraying geopolymer, much like other cementitious technologies, really falls into 2 categories. Centrifugally casting the product, spin casting, as some would say, or hand spray. So what you see in the pictures on the left are a couple of options for the spin cast process. On the right-hand side, you see the hand spray application. So note that on the right-hand side, this is maybe a little difficult to see, but it's a non-circular pipe. And oftentimes that's one of the driving factors to move a project towards hand spray rather than centrifugally cast, as it's much more difficult to maintain a uniform thickness when you're spin casting in a non-circular pipe. However, that's not to say it can't be done. And when we look at those projects, we look at the productivity associated with each and offset, and then compare that to any offset that you may see, any savings or lost additional cost to have more material on areas of a non-circular pipe than you may need for the design calculations. So typically, centrifugally casting is a more productive, more cost-effective process. However, in non-circular pipes, and in other cases with circular pipes, if there are many lateral connections, significant offsets, voids, those all need to be handled a little different than just showing up and installing product. We'll get into, I think we have 4 or 5 case studies here we can talk about. The first one is Lucas County, Ohio. So this was a project that was bid back in 2017, I believe, the first phase anyway. There's been several phases since. The reason why I like to showcase this product is that it, although not a design build, a progressive design build, project. It was a true bid build project. But the owner issued the solicitation somewhat open. It was the contractor's choice whether to rehab this pipeline using CIPP, slip lining, or geopolymer. And in our case, having experience in all the technologies, we were able to provide that evaluation, looking at all of those factors. What is the existing surface? What degree of preparation is going to need to take place? What is the bypass for each of the solutions need to be? What's the risk associated with the bypass? This particular system is one that sees a significant change in flows during wet weather events. So that all rolls into the risk register as we price jobs. Thankfully, we were low bid on the project, executed it with Geopolymer. As it says on the screen, this is roughly 1,800 feet of 90-inch diameter circular pipe leading into a treatment plant. So, talked a fair bit about bypass. This is one that required a design of at least 9,000 gallons per minute. As I said, we saw quite a bit of fluctuation from there, but at the end of the day, it all worked. What we needed to do to handle the flows is install an above ground bypass system. We'll talk in a few minutes about, again, the flexibility of the Geopolymer system and the capability of using internal bypass in some situations, but this one laid out really well to install a large overland bypass system. What we had to do to achieve that was install a 96-inch diameter shaft to insert vertical turbine pumps. You can see in the picture on the right-hand side there. And this note-about became a permanent structure throughout our project and working with the owner. The idea came to mind to facilitate future phases of rehabilitation to take this casing that was installed and turn it into a manhole structure. So we worked with several design engineers. We actually utilized the existing casing. We applied geopolymer to the inside of that and turned it into now a permanent structure. So I think last slide for Lucas County. The left-hand picture shows what the pipeline looked like after it was pressure washed and ready for the application. So if you can see in the video, there's a couple of grout pokes. There's a little painted spot here and a couple of other areas where some grout did need to be injected in order to stop some leaks. On the right-hand side, not the greatest picture, but you see what the finished product looked like.
Well, and Mike, before you go forward, I think it's really nice to point out, you can see in that last picture that is, you can see in both of these that this is not a straight pipe. So one of the key advantages of these technologies is, you can kind of maneuver these curves really easily without any issues, especially on something this big.
Yeah, that's a good point, Joe. And bends don't always mean that hand spray needs to take place either. So this was a triple cast project, albeit there may have been some hand spray work, but for the most part, long radius bends like you see in the videos, spin casting is still an applicable method of installation.
Yeah, and this was an 1,800 linear foot job that was done from a single access point, 1,800 feet. You were lining all the way in 1,800 feet back with just going from the one direction. So you can do a fairly long run.
Correct. Correct. There's a number of factors to consider when you try to set up something like that. It can be done. This is evidence of such. Lake County, Illinois is a nice one I like to follow up with regards to the versatility and the bypass. So much shorter pipe and only 100 feet long or so, but bigger diameter arch culvert. What you can see in the video is the bypass, or in the picture is the bypass routed through the pipe. What you can't see is the coffer dam So this went from a pond into a stream underneath a heavily traveled road in Lake County, Illinois. Between permitting, environmental impacts, and other factors associated with bypass and trying to take that pipe over the road or cut through the road or drill under the road, it just made a lot more sense to run the bypass through the line as you see in this picture. Another thing that makes this difficult to see in the picture is that there are blocks underneath the pipe so that it can be moved when you go to, after you've sprayed the first pass. So what you can see is our applicator hand spraying the first coat in the left-hand picture. On the right-hand picture, you can see it after it's installed. And what needs to take place in order for that to happen is that the finished thickness is applied everywhere that can be reached. So around those blocks that are supporting the bypass pipe. And then the pipe is jacked off of the blocks are moved onto the completed lining. And then, based on the self-bonding, homogeneous healing properties that Joe talked about, we can fill those voids where the blocks were. Now, again, very versatile. It's not the most productive application to route bypass through the line, but certainly when you have overland constraints that we experienced in this project and many others, some even we're currently working on, it's an advantage as compared to a CIPP liner, for instance, where all of the flow needs to be stopped and rerouted for the duration of the installation. Just to set your expectations as well, this photo was taken 1 year after. I think this was taken by the county, by the owner, as they took a canoe, I believe, or someone's kayak through the pipeline to inspect it. It's just a snapshot of a video. You see some staining on the sides, as you will see, of any cementitious material, be it new pipe or Portland or whatever, after some time. What you don't see and what was not evident in any of the videos or during this inspection were any structural concerns. So it's not always going to be a very pretty pipe like you see in the right picture, but structural sound. Region of York. This is the one Joe mentioned quickly earlier. This is 16th Avenue, 5,000 feet between access points, 104-inch diameter pipe, and severely deteriorated conditions. We talked about infiltration control. I don't know that there's a term that you can use greater than gusher, but that picture on the left-hand side would fall into that category if there were one. The right-hand side, you see large voids, pipe had decayed, had broken. So all of these things needed to be managed in conjunction before and in conjunction with the application of the material. Again, like Joe said, another challenge here altogether is this pipe is roughly 150 feet deep. So you can understand why there is such force given that potential head pressure in the water and the infiltration shown there. So pressure washing, again, a lot of manual handwork to remove any settled debris. Waterproofing comment is related to the infiltration control. Several different varieties of external grouting were needed, and I say external because you're drilling through the pipe from inside the pipe to the outside of the pipe to control that infiltration at those locations in order to apply the material. We did end up spin casting a large portion of this, hand sprayed some as well, and this was all performed while bypass in place behind this head at a 4-inch thickness. Very challenging project, but would have been more challenging with other materials. I think we have two slides out of order here. Another project we wanted to showcase today is the San Diego County Water Authority project that was recently completed earlier this year. This is the first aqueduct water pipeline. Joe mentioned it briefly as well when he talked about the Geospray 61 NSF certified product. This one included two 72-inch tunnels. There was actually a third as well that was completed via slip lining. This was a progressive design build project. So there, in the PDB format, there is much more time, obviously, than in a bid build process to evaluate alternative technologies. That evaluation, I can tell you, was extensive, and I don't think there's a technology that wasn't touched when we looked at rehabilitating these tunnels. Joe said this is a finished water gravity system. They did have some infiltration issues, horseshoe shaped, and you can see that a little bit better in subsequent slides here. In this application, the Geospray product made sense, was the right product for the job, as I mentioned earlier. On the left-hand side, you can see some repairs being made after a first coat pass, and that will happen periodically, handling the infiltration control, and you can see some additional grouting, some additional mortar applied. The right-hand side is the finished product. Great picture, great spin cast project. So with that, I think that's the last. Joe, do you have anything to add to San Diego here or any of the others?
I have all kinds of things if you want me to add them, but no, I think these are great projects. I mean, I think the 16th Avenue project is a real testament and a challenge to the capabilities of Michels as well as the capabilities of materials. I think, you know, that was looked at from a slip lining perspective as various other things. I think it would have required 3 or 4 additional shafts, which nobody was interested in building. 3 or 4 additional shafts would make spray applied lining it way easier too, but you didn't have to get there. I think the San Diego Water Authority is a really, really key project. There were really tight timelines on there. There were 3 10-day shutdowns. I think all of it was finished well before the 3rd shutdown was completed, which is critical there. And again, you were pumping materials 8 or 9 or 1,500 feet or so in, you know, from access points, so it gave you a lot of good opportunity.
Yeah,
So,
that critical piece I forgot to touch on. The one line was roughly 3,100 feet. That's quite a way to the pump.
Yeah, you did 3,100 feet from either side. Mike, there are some comments that people are having a little bit of trouble hearing you here and there, but we've got a bunch of questions, and I think I'll try to ask them and then go through them as people have them. If you have more questions, put them in the chat. We've got plenty of time for questions. So the first one says, can you use a geopolymer lining for a portion of a gravity sewer that passes through a tunnel, which is approximately 4 feet by 6 feet? The sides of the tunnel are made of concrete, the roof's made of rock, not very smooth. Would the geopolymer bond to the rock? We're really worried about infiltration. So I'll start with this, and I'll let Mike fix anything he thinks he doesn't like that I say. The answer is sure. That's one of the key advantages. If you were lining some sewer and you went down to another section that's different size, specifically if it's smaller, that can be a real problem for your projects. So we can solve that problem here that way. I cannot promise you that it will bond super well to your rock because I don't know what the chemistry of your rock is or whatever else. But the way we would typically handle that is if it was a roundish structure, and I don't know if this is kind of round or if it's boxy. If it's boxy, what we would probably recommend is you put some welded wire across the top to really hold that in place, anchor it into the rocks, and then you just go from there. So, I mean, there are ways to handle that. Some of them are more costly, some of them are a little more difficult, but they can work either way. We've seen several of those projects. I've seen several where it's like a rock arch for some piece, and then somebody installed a corrugated metal pipe on the outlets of those arches, and back and forth and things like that. So those are definitely doable. There's another question around expansion and contraction as compared to concrete. I'll also take this one. There's a lot of materials questions, so sorry, Mike.
No, that's okay. That's okay.
I think, you know, expansion and contraction is very similar to normal concretes. It works really well in those systems. It's typically going to have significantly less shrinkage because it has less water usage in the system. But from in terms of thermal expansion and thermal contraction, it's going to be very similar to most other cementitious materials. There's another one kind of broken up across a couple that says, can you add glass fibers to the systems to replace GFRCs? I mean, in theory, you can. The question is, do you need them? Because that's obviously going to add cost. You won't be able to do it in a centrifugal casted fashion, but you can make some of these. We've tested them with some of the people. You can make some heavier things. It's really about, do you need it? Is it really required for the design? And what benefit does it give you? And then what's it do to the impact on the application processes? You will not be able to push the glass fibers necessary to really get a glass fiber reinforced material as those are defined through some of these centrifugal spin heads. You will turn them solid really fast. But you can do it with a hand spray process and chopper gun at the application point if it's really necessary. But to be honest, we haven't really seen that needed in most cases. There's another question, I think, that's about the quality control, which was, how are these tests related to or representative of a thin liner? So what I would say is the quality control tests that are done on the field, one, you should be measuring thickness of the liner. Two, you should be measuring the physical properties of the material that you've mixed, because that's important for you to know what the physical properties are, so that you can ensure that the physical properties based on your design are what's in the system. Now, the question is, are those representative of a thin liner? The flexural strength measured on a 2x2 beam is pretty close to what's really measured in the system. You can't core samples out of the liners. And there is another question, like almost right after this one, that says, what's the thickness of the liners typically? So these liners will range from anywhere, let's call them like an inch thick in a 36-inch 1 meter application, all the way up to 4 or 5 inches if you're up in the 22-foot range with steel or other things, depending on what you're doing. But they're almost always curved, right? So if you take a 2-inch lining on a 96-inch pipe and you try to core it, it's really hard to test, because if that pipe's corrugated, now you have to cut out all of the corrugation. You got to get it flat, and your sample size shrinks really small. But we're really trying to get those physical properties of the material, and then all of the testing that we've done on repaired pipes in load frames are really to try to help show the design methodology and where it's going. You got any comments on that, Mike?
Not a lot, Joe, and I apologize to those of you I'm looking at the chat now who had an issue hearing me. I'm trying to project my voice a little bit more. A microphone issue apparently today, of course, of all days. I would back up to the first question, because I do get a lot of questions about bonding to hose pipes in general. Keep in mind, we're not relying on a bond to the hose pipe in most cases, especially in the case of a circular pipe. But we have experienced problems in the past applying the material on any sort of a smooth bore pipe. So you do need the material to stick long enough to cure in that shape to apply subsequent passes. But the design in those instances is not based on bonding to the hose pipe. And then you said, about testing or thickness verification, Joe. I mean, things that I've seen in the past is during the application, which I didn't touch on that, I probably should have previously, is that whatever the design thickness is, there's a number of different ways to verify you're putting on the right thickness. I've seen some so significant as measurements, even LiDAR inspections prior to application, verified with LiDAR inspections post-application. The most common methods are tabs. So you would put tabs periodically in the length of the pipeline as well as radially to ensure an even, uniform, substantial thickness greater than the design, or at least the design. So other than that, no, I haven't seen anything else. I'm still kind of reading through some of the questions here.
No problem. I'll go through. I've been deleting them on my sign so that they disappear. It's been my trick. If the coating is applied to a pipe to be installed by trenchless technology after installation, will the lining wear or push out during the pipe? So I will say these are really repairing structures in the system. No one is using this. No one is installing this in a plant and moving it to an installation. So it would be like an unreinforced concrete pipe at that point, which is a good functional pipe in the ground, but it's really hard to move. So I don't think anybody is attempting that. And obviously, since nobody's attempting it, we have actually attempted to test the integrity of those things. That's what we've been doing on the side, trying to get good design equations for these materials. But I agree, that would be a big challenge. There's another question about what I think to be GW, which I think is groundwater sweeps running behind the liner. So these are, I think Mike said the right things. Maybe we should clarify. First question we talk about is bonding. So these are designed for non-bonding. That doesn't mean they don't bond. That just means that we don't rely on that, so we don't worry about testing it so much. And surface preparation can be greatly dependent for the bonding. But these are applied typically with high pressure methods to the system, and there is no annular space or area between the systems. So it is unlikely that you are going to get groundwater running between the liner and the host structure. That does not mean that you won't have groundwater running behind the host structure if you haven't dealt with that. And what you often see is like the problem you have in a pipe that's leaking, and Mike mentioned it when he talked about the installs, is if you fix one piece of groundwater leakage, all of a sudden it now moves 50 feet down the line. That's typically not because it's running down the inside of a reinforced concrete pipe. It's running behind that. The water's behind that pipe, and it's now found the next weakest point to come in at. And that would be the same issue, but you wouldn't expect, like with CIPP or some of the other things, if they're not close fit, you can get water running behind them when they're curing, and that can be an issue, or it can be resolved depending on how you're handling the CIPP, but that's not something you're going to see in these linings. And they're usually done in segments anyways, so it would pop up. I've never seen a manhole where it's like leaking out the side of the liner because it's much higher pressure applied than that.
And Joe, I'll expand on that a little bit. I have seen it in a lot of my histories with the installation of CIPP, and this is where end seals have now become common practice with CIPP installations, is that groundwater tracking between the host pipe and the liner. I've seen those instances plenty of times over the years, especially back in the old days when those weren't commonly utilized, where after lining, you may not see much infiltration prior to lining. After lining, you see that water tracking in the manholes between the liner and the host pipe. With the case of Geopolymer, I've actually seen exactly what Joe's talking about, where after the liner, the Geopolymer liner has been applied, you see more infiltration into the manhole, not the interface of the Geopolymer to the host pipe. So
because the
manhole obviously with other techniques in the manhole.
And like I said, we've got plenty of time for questions. We've got several more we're still going to answer, and we'll keep answering them until there's no one left to hear them, but feel free to add them. So the next one was, the general rule of coating applications is 90% of all failures are preparation and 10% are all product design and selection errors. Has this been your experience? Yes, we 100% agree. When you don't do a good job preparing the pipe, that's when you have problems. The good news is these things bond really well to themselves. So when you really screw it up, it's usually not as bad as some of the other things that you can have go wrong with liners and coatings of that effect.
Agreed. I mean, with the epoxy coatings that we install on manholes, for example, or even the Portland cement-based products that we would install prior to the epoxies, preparation. However, my experience with Geopolymer, still preparation, but because of its bonding to itself, because it's again more versatile, more flexible in the application. We're not relying on that bond in our design.
Yeah. The next one is about commenting on the roughness of the lining and the pre-lined pipe and capacity considerations. That, of course, is a great question. What we typically tell people is the finished lining, if you applied it to a smooth pipe, typically has a Manning's coefficient of something around 0.014 or 0.015. If it's untroweled, troweling usually costs more and can be a little more effort, and it's significantly, different. If you're hand spraying, you can push that down a little bit. If you started with a corrugated metal pipe that was up in the 0.025, you usually end up filling the corrugations across the bottom. Usually it's in much worse shape. Usually if you're fixing that, the invert's got a lot of problems, so the invert ends up a lot smoother at the end. You can fill the corrugations and push it all the way down to the 0.014 if you really need to. That also might create you some new problems with scour or velocities, so you may not want to do that. We have people needing to put fish passages in. But typically, if you start with a corrugated metal pipe, you end up with like a 0.025 and you gain, or 0.02 and you gain capacity, or 0.018, somewhere in that range. If you're on the smooth stuff, yeah, you will lose some capacity, and it can be an issue on really tight pipe designs, but in general, it's usually not that big of an issue. The next one is about, can these liners hold, let's call it modest internal pressures of 15 to 20 psi? They can, if you design them for that, and if the hose pipe has enough integrity to help support them, but they can. We've done several projects where people have done up to, big pipes up to 35 psi. These are not going to be standard AWWA class 4 pressure pipe linings. At best, they're class 3 because they're non-bonding. And we're trying to do some work to kind of evaluate the answers to that question, but they can definitely hire some modest force main pressures, as well as some gravity issues, because they're pretty rigid, so they don't have some of the gravity influx problems. Next question is, on a 96-inch diameter pipe, how thick would the lining be? The answer to that question is the answer to all questions. It depends. It depends on what your loading is and what your live loading is and how deep of a bury is. But a rough estimate on a 96-inch pipe, if it's at the perfect bury depth with very little live load, you might get away with 1.5 inches. But my guess is most cases it's going to be closer to 2. But it would depend on the design. Can the geopolymer be sprayed into vertical structures, manholes, and such? What's the minimum diameter of vertical spray in millimeters, Mike, is their question.
Well, I'm going to forego the millimeters part of that, but absolutely can be installed in vertical structures. We've done quite a bit of it. In the Lucas County example, that was a 96-inch diameter shaft. We created a manhole access point out of it. At that point, as far as the minimum diameter, it all comes down to the contractor's equipment. What you can spin cast manholes as well. There's a number of different tools on the market to handle those things. Generally speaking, I would like to believe that a manhole is not going to be less than 2 foot in diameter. Otherwise, it would really be a good access point. That should be just fine. Commonly in my marketplace, 36 inches about the minimum, and the number of 42, 48, 5, 6 foot or more common on big diameters. So.
I've seen some down as low as 18 inches. That, I mean, the problem if you line an 18-inch manhole and you put a 3/4 inch lining in it, it's now a 16-inch manhole. But if it's a structure and you need it for some reason, maybe it's not actually a manhole, but it's an access for pipes or some other tools. Yeah, but it's really about the equipment you have. As long as you can get a spin head in there, you can spray it. The question is, what will you have when you're done? And you know, we don't see people doing it much less than 24 inches, but it can be done. I've seen it done all the way down to 7 inches on a pipeline. So you can do it. It's just a matter of, can you stop the infiltration? What are the processes you're using? What are you doing? The next question was about, are there any advantages or disadvantages or complications when using the HCE or the Geospray 61 product versus the regular Geospray? So the difference between Geospray and Geospray 61 is pretty simple. It's a lot of paperwork and it's a lot of chemical testing, but the products are basically the same. It's really just around dealing with that. I'll let Mike comment, but we think from our standpoint, most applicators could switch bags between the three and not really notice what they were doing. Maybe there's a slight amount of water change you might need for one or the other, but they all behave very similarly. They all have similar processes. There's just some formulation change to the HCE product to give it additional chemical resistance that's required in some of the most aggressive applications.
Yeah, the workability of the product is nearly the exact same across the board. So, I mean, maybe a little bit different when you get into some of the equipment needs for a 61 product, but the actual mixing and application is virtually the same.
Yeah. The next question's asking about the fact that we don't have a standard design philosophy. Do we have specifications worldwide that cover the use of the design? And I would say absolutely. So there are specifications all over the world for these materials. Everywhere it's possible, we have tried to put in some design guidance into those specifications or minimum design requirements based on the actual testing that we've conducted. And if you want to do something else, you can, as long as it's more conservative than that. So there is a whole bunch of those things. Our contact information is up on the screen on those QR codes. I'm sure if you Google either one of us, you'll find us really quickly. We both have LinkedIn pages. If you need something, send us an email, send us a note. We will be happy to find you the right specification for your region. That's good with that one. Someone asked if the recording will be available. Yes, it will. The next question says, in Texas, the main issue is humidity and temperatures required for applications are so restrictive we end up having to wait days, if not weeks, for a time where they can work be done. Any suggestions? The good news with these linings is temperature and humidity we really like humid. So temperature and water, as long as it's not leaking in active flow, these are good situations for a spray applied geopolymer system. So we would really have to, we'd have to really understand the issue that you're running into for what the suggestions would be. But there are definitely technologies that have those problems where you're fighting weather. One of the key advantages that we didn't discuss is these materials, you can generally release bypass, and this is a general rule, 3 to 4 hours after you're done spraying, sometimes less, sometimes a little more, depending on the weather conditions or the types of flow you have. But if you can walk on it and not leave a footprint, you can pretty much release water. And that, gives people all kinds of flexibility, because the worst thing that happens is if you have a rainstorm, you lose an hour's worth of work, not a large CIPP bag stuck in the system that you couldn't cure. So you don't have to, you can work around weather a lot more with these systems, and we'd be happy to reach out to you. We can see who asked the question, so we'd be happy to send you a note and have somebody talk to you about specific applications.
Yeah, the one thing I would add to that though, Joe, just because it's probably for the benefit of the larger group, temperature, Joe said we love humidity, absolutely. Temperature can be a challenge, especially in extremely hot areas. We've installed in 105-degree weather, we've installed in 20-degree weather. The heat you absolutely need to pay attention to, depending on the setup, depending on the work site. There are things that can be done to mitigate that so that the material doesn't cure too quickly in the houses. But to Joe's point, specifically, we can reach out to you who asked this question and understand the problem a little bit more.
No problem. I think I've got two more questions on there. One's around what's the pressure rating of a geopolymer pipe, for example, 36-inch. Like, you would have to design it, but I think the question earlier, modest pressures less than 35 psi kind of force main type applications are kind of the limitations of these linings, unless the hose pipe is, you can use it in a pipe that has higher pressures, but it's not going to be the pressure rated portion. It can stop exfiltration, it can plug holes, but it's not going to be the standalone structure. If we were designing the coating for pressure, we would look at a different approach to the math. We'd be happy to talk with you offline on what we do, but there's thin shell pressure applications that we would look at based on the tensile strength. And it will increase the liner thickness depending on what you're trying to do. The last one I have, Mike, is really for you. What's the minimum project size Michels would like to bid? I'm sure he's not going to answer that.
No, you're exactly right. It is too many factors to answer that directly. So rather than giving you a long-winded indirect answer, if you would take my contact information and feel free to reach out to me with what you're looking at, I'd be more than happy to have a personal conversation.
And with that, I don't have any more questions. I'll leave it for a second if somebody is rapidly typing one into the chat. Otherwise, we'll have this available after the webinar. I think it'll be available at some point fairly quickly on Michels' website. It'll probably be available on GeoTree's website. We're happy to answer any other questions and follow-ups. Our contact information are on the QR codes on the screen. And if you leave the webinar, you should be getting a survey email or survey and an email about it. So we really appreciate all the people that attended. And if we can answer any other questions, you know where to find us.
Thank you so much, everyone. Have a great day.
Thank you.